Vanakkam. Welcome to this video on biomechanics. We have been looking at biomechanics of soft tissues in the past week. Specifically, we looked at biomechanics of tendons. We also discussed how tendons interact with other tissues and tendons interact with other tendons. There might be, for example, shear that might happen between tendons. Or we also looked at a case when one muscle gives rise to multiple tendons, and if the muscle is contracting, all these tendons might simultaneously contract. So, there are many complications like this. So, where one muscle is contracting, all the tendons are contracting, or different tendons are connected to different compartments of the same muscle, or different tendons are connected to different motor units of the same muscle, or one motor unit connecting to multi-digit or multi-tendons. So, one motor unit gives rise to or muscle fibers of one motor unit attach to different tendons. So, remember, one motor unit is the set of one motor neuron and the set of all muscle fibers are connected to that motor neuron, is it not? Set of all muscle fibers. So, if that muscle fiber, if there are say 100 muscle fibers connected to one motor neuron, let us say 40 of them connect to tendon 1 and 60 of them connect to tendon 2. Whenever this motor unit is firing, these 40 muscle fibers connected to tendon 1. So, tendon 1 will also get pulled with some strength, tendon 2 will also get pulled with a different strength. Right. Many of these complicated situations happen. One particular example of such intertendinous interactions or between tendon interaction happens in the case of human fingers, because we have multi-tendon muscles that give rise to many tendons and connect to different fingers. Because of this reason, probably because of this reason, forces produced by fingers are somewhat dependent on each other, and movements produced by fingers are also dependent on each other. The question is, forces and movements that are produced by the fingers, if they are dependent on each other, is it purely due to mechanical factors, or is it purely due to neural factors, or if it is a combination of the two, can we dissociate the amount of contribution each of this is making? This is a relatively complicated topic. So, we will unpack it as we go along. I am just introducing what the topic is, the broad topic in this. So, we will discuss. So, from this week, we take a step upwards and discuss some research papers. Okay. We go one notch higher and discuss some research papers. As a first paper, we discuss the work by Vladimir Zatsiorsky, Zhongming Li and Mark Latache on enslavement in force enslavement, published in year 2000. Another paper is from our own lab at IIT Madras, our neuromechanics lab at IIT Madras, between co-authored by me with my past dual degree student Niranjan Chakrabavi. We discuss kinematic enslavement and the possible role of wrist posture in affecting kinematic enslavement in that paper. Okay. So, in this video, I will introduce the notion of enslavement, and I will discuss the background on enslavement, and in relatively good detail we will discuss the research paper on enslavement, which is enslaving effects in multi-finger force production, published in the journal Experimental Brain Research in the year 2000, authored by my advisor Mark Latache and Professor Vladimir Zatsiorsky, Dr. Z, as we respectfully and affectionately call him. Right. So, what is enslavement? So, when you move one finger, the other fingers also move. We saw this in one of the previous classes. So, keep your hand like this and do this exercise. Move only the ring finger. This was the task that I gave the other day. Now, I am moving only the ring finger. Is it not? When I move the ring finger with no explicit instruction to the other fingers, what happens is that the other fingers are also moving at least slightly. Okay. Now, this is some unwanted or unintended movement. A question is, what is the source of this lack of finger individuation or finger enslavement? Okay. When this form of enslavement, when it happens in the force domain, when you are pressing on an object, when you are holding this object, for example, when I am holding and pressing on the object, or when I am pushing or pressing on an object and doing some pressing task, force produced by one finger affects the forces produced by the other fingers. Also, force produced by one finger is affected by the other finger's forces. These are two different things. If the index finger is producing a force, it is affecting the force produced by middle, ring and little fingers. The force produced by the index finger in a multi-finger task, if 3 or 4 fingers are producing a task and I am only measuring the force produced by the index finger, the force produced by the index finger alone is not just a reflection of the intended force that is meant for index finger. Let me unpack that. What I mean is, in a multi-finger task, let us say I am performing index, middle, ring, little, with 4 fingers I am pressing on an object and I am measuring, say, all the 4 finger forces, and I am taking, for example, only the data from the index finger. This is not purely the result of index finger intention or force intended for index finger, but rather some spillover from the other finger actions also is reflected in the index finger. But I have only one measurement. I have only the index finger force. From this, I want to know what was the intended index finger force, how much of the other force is coming from force produced by the other fingers, spillover from the other fingers. Is there a way to measure? Is there a way to dissociate? These are the questions. So, relatively complicated topic. It appears like a complicated topic. It is not. We will slowly and patiently move through this paper, so you can upgrade yourself. We can upgrade ourselves and move to the next level in our quest, in our journey to appreciate and understand research in the field of biomechanics, because that is our goal. We started out at a low level, we are slowly moving up, right. So, when I ask one finger to produce a force, the other fingers are also producing an unintended force, right. That happens in adjacent digits, but also happens in far away digits, right. Now, if I give an instruction to produce a force with just the index finger or just one particular finger, that is the instructed finger. Let us say I am asking someone to produce a force with the ring finger. Okay. Now, that is the instructed finger or the master finger. By the way, there can be more than one master fingers. I can say produce this force with index and middle, produce this force with index and ring, produce this force with index and little, or middle and ring, middle and little, or ring and little, however it is. Likewise, 3 finger tasks, 4 finger tasks, all of these are possible. So, there can be more than one instructed finger or master fingers. Those fingers that have not received instruction, the instruction is usually to not worry about what the uninstructed fingers are doing. Suppose the instruction is to produce a force with these 2 fingers, right. Do not worry about what the other 2 fingers are doing, let them be, let them do whatever they want, do not worry about them. They may produce a force or they may not produce, don't explicitly produce a force. At the same time, don't explicitly stop them from producing whatever it is that they are producing. Okay. That is, I am explicitly interested in measuring what these two fingers are doing. This is instruction, these are the masters, but I am also measuring what these two fingers are doing, but I am telling the participant, the human participant, don't worry about what these two fingers are doing. In particular, don't stop them from doing what they are doing. Don't also explicitly produce a force, don't also explicitly involve them. Now, this is a relatively challenging task to perform. Actually, the task itself is easy, but this is a relatively challenging experiment to perform. If you tell someone to not do something, it's an extremely difficult instruction to follow for all of us, for all humans, something that all of you will relate to. Right? When you tell someone to not do something, they will do exactly that. Right? For example, while you are taking this medicine, you take this medicine, and while you are taking this medicine, don't think about the monkey. It's extraordinarily hard for you to not think about the monkey when you are taking that medicine. That's this joke that floats around, right? It's extraordinarily hard to, because the instruction usually, right, when this is something that my colleagues and senior professors told me, when you instruct your students, tell them what to do. Tell them, submit the assignment by this date. In particular, avoid telling them what not to do. That is, it is better to not tell the students, please don't delay the assignments. Okay. If you tell them, please don't delay the assignment submission, it is very likely that they will delay the assignment submission. Tell them what to do. Please make sure that the assignment is submitted by, say, March 25th, some date. By that date, please make sure that you submit. Tell them what to do. That is, in this particular case, that's a very difficult instruction, because you are telling them not to worry about what the other fingers are doing. That's a very difficult instruction to interpret. What does it mean, not to worry? Should I worry or should I not worry? Should I follow that instruction or not? Should I completely ignore those fingers, or can I also involve those two other fingers? What does it mean to not worry about the other two fingers is not clear, and different people are likely to interpret it in different ways. So, do not worry paradigm, do not care experimental paradigm has this major disadvantage, where it is not clear whether a particular participant followed instruction or not. You tell someone to do something or not do something, how do you know they followed your instruction? You actually don't know, you assume that they do. These are humans who understand the language that you speak and who want to help you, who are sincere, and they are following your instruction. But it is entirely possible that a well-intended and sincere human also does not follow instruction, because they simply don't understand the instruction. Even if they understand the language, they don't know what it means, the deeper meaning. There might be many reasons why this might simply not work. There is a way ahead, there is a way out of this. We will discuss that in the rest of the discussion. There is a way to avoid this, there is a way to account for this. Okay. This is the major challenge in this type of instructions and experimental paradigms. Okay. Let us discuss this in much greater detail in going forward. So, let us say for example, you have a button press task like the one that you have, press with the index finger. The instruction is press the button with the index finger and don't worry about what the other fingers are doing. By the way, in all these experiments, it is very important, it is absolutely crucial to measure the forces produced by all the four fingers. Okay. You measure all the four finger forces, but the instruction is only for the index finger, only for the master finger, not necessarily index. Whatever is or are the master combinations, right? You measure everything. Let us discuss this in some more detail. A question is, what are the hypothesized reasons for enslavement? A question is, what is the cause of enslavement? We discussed this in the previous week in some good detail, but let me try and refresh this. Okay. What are the hypothesized reasons? We said at least 3 different reasons for this, right. One is there can be mechanical coupling between tendons. There can be shear, force transmission between tendons and other such things. There can be, when one tendon is moving, the other tendon is also moving purely because of mechanical reasons. Mechanical coupling between tendons, that is one possibility. The other possibility is the existence of multi-digit motor units in the extrinsic flexors and extensors of the hand. This is what is multi-digit, multi-finger. So, one motor unit is the set of all muscle fibers that are connected to a particular motor neuron. If these muscle fibers, let us say there are 1000 muscle fibers under discussion, say 400 of them connect to tendon 1 that goes to the index finger, 300 of them connect to the middle finger or ring finger, 200 of them connect to the little finger or middle finger, and 100 of them connect to say the ring finger or the little finger, whichever way it is. Say for example, let us say 1000 fibers connected to a given alpha motor neuron. A given alpha, this is the key. One alpha motor neuron connects to say this 1000, it is an example number. One alpha motor neuron connects to this 1000 fibers. Okay. Now, of this 1000, say 400 of them connect to index finger tendon, say 300 connect to middle finger tendon, 200 to the ring finger tendon, and 100 to the little finger tendon. Well, actually it does not have to be this way. I mean, it appears as if there is a gradation 400, 300, 200, 100. It does not have to be this way. Okay, let us say some different numbers. The sum must be 1000. Let us say for example like this. It does not have to be exactly 400, 300, 200. It is an example. Okay. Now, remember that whenever an alpha motor neuron is firing, all the muscle fibers connected to this alpha motor neuron will fire. This is the rule, because the neuromuscular synapse or the neuromuscular junction is an obligatory synapse. That is, whenever the alpha motor neuron is firing, the muscle fibers will produce an action potential and contract. This is a known fact. So, that means whenever this alpha motor neuron is firing, this 1000 fibers, all of them will get activated, but they will have differential consequences on the 4 fingers. Why? Well, actually assuming these 1000 muscle fibers need not be of same force producing capacity. That is a different discussion. It might be that different muscle fibers have different force producing capacity, and because of that the forces might change. That is a different discussion, but let us assume that all these 1000 have very similar or same force producing capacity. They are uniform, they are all the same, they are all identical, they have similar force producing capacities. For the sake of discussion, we will assume this. Now, when this alpha motor neuron fires, all this 1000 muscle fibers will fire. That means if 100 units of force, let us say 100 millinewton or whatever, let us say some 100 units of force is produced by the little finger, then 400 units of force will be produced by the index finger. If this was the only tendon, if this was the only force or if this was the only motor neuron and the muscle fibers that are contracting at that time. Let us assume that this is the only motor unit that is contracting at that time for the sake of discussion. So, many assumptions we are making. If this was the only motor unit that is contracting at that time, then the force will be distributed like this 1:2:3:4 between little, ring, middle and index in that order. Is it not? That means if the instructed, it does not matter what the instructed finger is, right. If the instructed finger might be the ring finger, it does not matter, or the instructed finger might be the index finger, it does not matter, because this alpha motor neuron is activated, all the fibers will get activated because they have no choice. They cannot say, oh, only the index finger has to produce force, why should I contract? That option is not there. They have an obligatory synapse, it is an obligatory synapse, so they will produce force. The real situation is actually a bit more complicated. There are many motor units and there is quite a bit of distribution. Okay. The point is that there are these multi-digit motor units in the extrinsic flexor and extensor muscles that may or may not originate from different compartments. There is also muscle compartment complication that we are not discussing as part of this discussion. They may originate from different compartments, for example. There are quite a bit of complexity involved in this. The point is that this may be one of the sources of enslavement. Going back, our original discussion was what may be the cause of enslavement. First we said that peripheral mechanical coupling between the tendons, shearing, force transmission and other such things, merely because one tendon is transmitting some force to another tendon, maybe due to shear, lateral force transmission, something is happening, and because of that there is some force transmission that is happening tendon to tendon, right. That is one. That can also happen because these tendons move in close proximity with each other. This is one of the possibilities. The other is that multi-digit motor units. Remember in the last week's video we discussed how in a given region of the brain there might be neurons that might send commands to different fingers but located close to each other. So, two neurons that are neighbors to each other, that are next to each other, adjacent to each other, may actually end up sending commands to fingers, index and little, fingers that are far away from each other. This is a possibility. We discussed that, right, saying that there can be a mosaic arrangement of finger representation in the motor cortex. Also remember that, also one more thing to consider is that these neurons are usually, corticomotor neurons are those neurons that have a monosynaptic connection with the alpha motor neurons that supply to the hand and fingers, okay, something that is discussed in much greater detail in my other courses. The point is that if a particular region of the brain corresponding to the fingers is activated, it is likely that if that region is activated, let us say a region of the brain is activated, then many different neurons that supply to many different fingers will get activated. Because of this reason, it is likely that the fingers will also produce force differently, not because of mechanical reasons, but because somebody sitting up there, I mean I am oversimplifying that situation. The neurons in the motor cortex are sending commands to diverse regions, a bunch of regions that may be far away from each other, okay. Diverging central commands is what is the other reason that we discussed. So, the first cause is this, where the tendons may shear, for example, with respect to each other. The other cause is this is also the same, again showing the tendons this, and this is the second cause where this motor unit is applying to different fibers that may connect to different tendons, okay. These are the three hypothesized causes of finger enslavement, okay. But our question is not this. Our question is, can I understand or identify or dissociate which of these causes is a major cause, or which of this is contributing to the enslavement in a great way? Can I do that? That is the question. So, these are the possible reasons for finger enslavement. Our question is, which is causing more, or which is contributing in a greater manner or to a greater level for this phenomenon. To study this, we will have to discuss these research papers, but for now we will end this video. So, in this video we looked at the definition and what is finger enslavement, and we discussed that in good detail, and we also discussed the hypothesized reasons for enslavement. With this, we come to the end of this video. Thank you very much for your attention.